Yeah, I can. Okay, this is working now, I guess? Okay, so good morning. I'm Thibault Simon, and I'm a PhD student at Inria Lille in the Pierre Rust team, and I'm also employed by Orange Labs, which is the building at the next metro station. And today I present to you the work we did on software lifecycle environmental footprint together with my PhD advisor, Pierre Rust, which is here, and Romain Rouvoy, as well as Penhoat, which is a colleague from Orange Labs. So ICT environmental footprint, I'll give you a few non-exhaustive list of these impacts because it has been said already before here. But basically, GHG emissions have been talked about a lot, including their consequences this morning. But what I would say is that the sectors, even if it grows or not, is not really aligned with the Paris Agreement that was talked this morning, and the current trajectory is not the right one. Now, ICT also require rare earth materials, which extraction harms the local population as well as the environment. Now, finally, on ICT environmental footprint, while ICT devices end their life, they become e-waste, which a small part really is collected, and even a smaller part is very recycled, and it often ends like this. So what I would argue is that while the ICT environmental footprint comes from the hardware side, the responsibility lies within the software, because software makes hardware run and use energy. It is software that consume more and more hardware resources for even more needs. And finally, part of the e-waste that I've shown before is driven by software. So what I did is that I wanted to see how the literature as well as standards consider this software environmental footprint. And what I found is that, well, it mainly focuses on a single impact categories, climate change, through GHG emissions. It often considers only the energy which is consumed by resources, by hardware resources, and omitting their embodied impact, which is due to their manufacturing as well as end of life. And finally, the standards of literature often focus only on the software usage phase when it is used on, but they often omit the development phase of software. So to tackle these lacks, I used the benefits of a life cycle approach, which is basically, I'm sure that most of you are familiar with this, but a life cycle analysis basically and simply is the analysis of the contribution to the environmental impact of a product across its complete life cycle, ranging from manufacturing, usage, and end of life, and other phases across multiple impact categories. Now, there are two benefits. There are more than this, but there are two benefits of using such a holistic approach. That is to identify the shifting of potential environmental burden across two things. The first one is between phases. Now, think about electric car, for example. If you replace your petrol-powered car by an electric one, then the usage phase, at least in France, will reduce, but the manufacturing as well as material extraction phase impact will increase. Now, another kind of shifting that can happen are between impact categories, such as, for example, if you switch your energy generation from a coal power plant to solar-based one, then you will probably reduce your climate change impact while increasing water depletion or raw materials impact due to the manufacturing of these solar panels. Now, what we did is that we wanted to see what kind of outputs we can have by using such a holistic approach on software. So quickly, what we wanted to do was to find a flexible way to adapt to each software context, because software are very different from one another, their life cycle are very different, and we wanted to find a flexible, while simple way to model this software lifecycle. So basically what we did is that we used a tree representation where each node of the tree represents an activity, a phases, we call it how we want, if you want to match the LCA vocabulary or not, if you want to adapt a little bit, that it's possible. Now, the idea was to keep a common computation methodology despite the variety of life cycle. And we consider that to be achieved, each of these phases or activities needs resources to be achieved. So for software, the first resources that we think about are hardware resources. They are virtual machines, they are servers, they are storage, etc. But there are also some other resources typologies that are consumed while developing software. And here I show that, for example, the people that work on this software have an associated environmental impact. And what we did is that we gathered an exhaustive typology of resources and their associated impact that can occur during software the software footprint, software life cycle, sorry. And for each of these resources that we gather the impact, we gather the impact on multiple categories because, as I said at the beginning, climate change isn't the only impact of ICT. And quickly, what this shows here is that, for example, if you take the impact of one people that comes to work from one day, then these people will use other resources such as a laptop, monitor, an office, which uses electricity, but it will come to work using its car, public transport, etc. So these resources uses themselves other resources. And so using this way, what we can do basically is that we can compute each phase or activity relative impact thanks to the resources that they consume, and then we can obtain the overall life cycle impact at the very top of the tree. Now, I said earlier that the benefits of such an approach is to uncover impact shifts, and to apply this methodology, what we did is that we took data from the GitLab project, open source project, as this will not be the footprint of GitLab, but rather representative of its size and complexity. And what we did is that we applied a post-mortem approach using Kokomo, which is a methodology to estimate the effort which is required to build software, to estimate the effort that was required for the building phase of GitLab. And for the usage phase, we used the hardware requirements for the biggest instance possible. And we used the factors that correspond to hosting and development in France. And now quickly, because I ran a little bit out of time, but the kind of shift that we can see here, the idea is to look at orders of magnitude rather than absolute value due to the imprecision of reference data. But basically, we can see here that on our sampled use case, well, the build phase is a very large part of the impact, and it's largely is more than the running phase one, which we would not have seen if we did not take a lifecycle approach on software. The second one is between resources. We can see here we changed the thing because I think we can all agree that software cannot really be GitLab will software this side will be hosted simultaneously on multiple sites. So its usage impact will be much bigger. So what we did is that we evened the build and run impact at the tipping point where the build impact is at 50% and the run impact is at 50%. And what we see here is that using a holistic typology of resources show that, for example, on the overall software footprint, the car impact is really there and really important, which can be a little tricky. Now, the other thing to see here is that for storage, for example, without considering its manufacturing impact, we could not actually have seen it as a big source of impact due to its low usage, energy consumption, but rather big manufacturing impact. So I will just skip this one, but the idea is basically do not focus on CO2, consider the other impact categories. We proposed a web application that will soon be available open source on the Orange repository, but is going on bureaucracy things right now. But it allows each and everyone to model their own context, because all the things that I presented here are already dependent of the context and they are not generalizable. So finally, to conclude quickly, what we did is that we developed a methodology and the associated to model a software lifecycle environmental impact. And the idea is to identify shifts as well as hotspots to take the right decisions to reduce this software environmental footprint. And the last key idea is that it was hard to gather resources. They are imprecise, they are average, they are not really good, and the ecosystem pretty much lacked the data on the resources it uses. So thank you very much for your attention.